Thanks, Wes, for giving us this seminar. And I would like to introduce Wes, and we are former colleagues back in Mississippi State University. We worked together for a number of years, and afterwards Wes left, and now he joined this DoD High Performance Computing Modernization Program. It's a PET, it's a training program, and continue doing these high performance computing work, specifically in the artificial intelligence, how to apply this important technology in science and engineering, broad field, not just for computation. So we are looking for exciting presentation from Wes, and I also would like to thank Dean, Mike, and our chair, Mohammed. They are here for this presentation. Well, thank you, Wes, and thanks everyone.
Yeah, thank you, Chunhua, for that introduction, and thank you for the invitation to be able to speak today. So this is a topic that's been very exciting for me. And so in the next hour, I'd like to give an overview of artificial intelligence and show you how powerful it is and how ubiquitous it has become and how it's being used in science and engineering, what dangers it imposes. Can you guys still hear me okay? Seems like and where it's going in the future. You guys can still, hello? Okay, I can't hear you guys. That's weird.
Yes.
Okay.
I didn't want to.
Okay. All right. So AI is becoming ubiquitous. So you see it everywhere. So whether it's self-driving cars and object detection or natural language processing. So every time you talk to Alexa or Siri or Google Nest Mini or something like that, even every time you charge your credit card, machine learning algorithms are working behind the scenes to detect if this is fraudulent activity or not. Security scanners at airports use AI to automatically detect threats such as firearms and explosives. So because of this, Andrew Ng, who's one of the leaders in this field, has said often that AI is the new electricity. So he likens it to the electric revolution, when about a century ago, we started to electrify the world through electrical revolution by replacing steam-powered engines with those using electricity. We transformed transportation, manufacturing, agriculture, healthcare, and so on.
Well, sorry to interrupt you. We cannot see the slides.
Really?
We are seeing only your introduction slide, the first time.
That's weird. Okay.
Oh, okay.
Let me try this again.
It's just a blank screen here.
Yeah, I'm gonna share my application instead of the desktop. Stop sharing and share. Okay, how about now?
Yeah.
Okay. I guess you didn't like. So I guess you didn't see the last slide, which was it just showed an overview here of different types of how AI is being used in self-driving cars and for doing object detection, natural language processing, biometrics. And so Andrew Ng has said that AI is the new electricity. He likens it to the electrical revolution. And so he says, he has this quote, about a century ago, we started to electrify the world through the electrical revolution by replacing steam-powered machines with those using electricity. We transformed transportation, manufacturing, agriculture, and so on. And now AI is poised to start an equally large transformation on many industries. So with that, I'm just going to give a little overview of my talk here. So I'm going to give a little bit of an introduction to AI, and And we talk about different methods for doing AI. And then I'm going to be talking about two application areas for AI that I've been working in. And one is AI in medicine, another is AI in warfare. And then I'm going to talk a little bit about the future of AI. So we often hear terms like AI or machine learning, neural networks, deep learning, and sometimes it's difficult to know how these are interrelated in that. So actually before there was machine learning, there was AI. Some of the early systems were rule-based systems like chatbots. If you've ever used Eliza, the EMAC psychiatrist, you could experience this type of AI. But within machine learning, there are brain-inspired approaches, which I'm going to be mainly talking about, and then there are many different top categories as well, such as like decision trees, support vector machines, Bayesian networks, genetic algorithms, and that. But I'm mainly going to be focused on the brain-inspired machine learning, and then within brain-inspired machine learning, there's two branches, and one's the area of spiking neural networks, SNN, and the other is artificial neural networks, or ANN. And so the spiking neural networks attempt to use a more biorealistic approach and closely mimic neural networks in the brain. Whereas the artificial neural networks were inspired by the idea of how the neural networks work, but then used some practical mathematics such as gradient descent for back propagation, which makes it more practical to use in reality. So while overwhelmingly artificial neural networks is being used in most applications, there's still quite a bit of research going on to develop spiking neural networks that perform well. And so within spiking neural networks, one of the advantages is that they are highly energy efficient. So Intel has developed a chip called the Loihi neuromorphic chip for spiking neural networks. But in general, this spiking neural networks haven't gained broad popularity yet. And most of the work that you see in AI is in this area of artificial neural networks. And then specifically within this, there's an area called deep learning. And this is where you have many layers of neurons or convolutions or different kinds of layers that form these large neural network architectures that you can train on data. And so I believe it's this deep learning that has really caused AI to explode in popularity. But the interesting question is that AI has been around for like 75 years. So Alan Turing may have been the first person to start working on intelligent machines in 1947. And then John McCarthy coined the term artificial intelligence at MIT in 1955. So how did AI explode in popularity in just the past 7 years? I mean, before 2015, you really didn't hear the term deep learning. So there used to be a yearly competition in image recognition called the ILS-VRC, which stands for ImageNet Large Scale Visual Recognition Challenge. This came out of Stanford University. It's also known as the ImageNet Challenge, and that ran from 2010 to 2017. And they basically provided a really large data set of images with labels. So it's called ImageNet, and it provides 15 million labeled high-resolution images belonging to roughly 22,000 categories. So the ILS-VRC was one of the largest challenges in computer vision, and every year teams competed to claim the state-of-the-art performance on a data set. So you can see here the first year, 2010, and what these are trying to do is detect, if you have an image, detect what's in the image, and this is generally done using it'll predict based on probabilities. Like this is a cat, 86%, it's a dog, 9%, raccoon, 2%. like this. And so there are things called top 5 errors. So that means how well can you predict that the object in the image is going to be in the top 5 things that are predicted. And so in 2010, the errors were on the order of 30%. So I remember back at that time, people saying things like computers are really good at doing a lot of things, but they still can't detect what's in an image. They still do very poorly in detecting what's in an image. So what happened in 2012 is when the first group started using deep learning algorithms with convolutional neural networks. The first one was the AlexNet, who won the 2012, and then Overfeet 2013, and then GoogleNet in 2014. And what happened in 2015 is that with this paper called Residual Networks, or ResNet, it's a 152-layer architecture, deep learning architecture. It actually surpassed human level performance, which is, I guess, is around 5%. And so that's really when people started realizing the power of these deep learning algorithms, because now AIs were outperforming humans in detecting, telling what's in an image. Another big event happened in 2016 with this headline: Google achieves AI breakthrough by beating the world Go champion, Lee Sedol, from South Korea. And this is an area of AI called reinforcement learning. So why is this significant, and why is Go so hard? So in Go, there are more possible moves than atoms in the universe. Actually, there's a really good movie that I'd recommend you to watch if you get a chance. That's called the AlphaGo movie. That's the URL there. It's really interesting. But you might think that you could just take all the data that experts have used when they played the game of Go and train a neural network. The problem with using that kind of approach is you'll have an AI, but it won't be able to achieve superhuman performance. So they had to, they basically trained, the AlphaGo beat Lee Sedol, I think it was 3-2, if I remember correctly, 3 games out of 3. They won 3 out of 5 games. After the AlphaGo, they built something called AlphaGo Zero. So AlphaGo was built on using some data from historical games and also using some reinforcement learning where it was figuring out itself. They built something later called AlphaGo Zero, where they didn't give it any data, and they just the AI just learned how to play the game itself. And AlphaGo Zero beat AlphaGo 100 games straight. So it was a lot more powerful. So AlphaGo had to actually this AI had to develop some level of intuition. And so they were actually, if you watch the documentary, that they were, it was making moves that the team that developed AlphaGo didn't understand why the computer was making the decisions it was making until afterwards, much later, when they saw how it was, they were superior moves. So this is another example of AI achieving superhuman performance. This is a quote from Lee Sedol in Game 2. He said, yesterday I was surprised, today I'm speechless. In November 2019, Lee Sedol retired, stating AI is impossible to overcome. Now, this is the world champion in Go. Even if I could become #1, there is an entity that cannot be defeated. And then again in 2018, there was the headline, OpenAI's bot handily beat a team of professional Dota players. So this is an area called multi-agent reinforcement learning. So instead of playing against one player, you're playing against the top 5 of the top players. And then again in 2019, Google's DeepMind beats the professional human StarCraft 2 players, which is even a more complex game. So if you were to look at these, if we were to assess like AI progress through history, we can measure its progress based on how it's able to outwit humans in the most complex games in the world. So starting back in tic-tac-toe in 1952, and then yeah, going through here, Connect 4, backgammon, chess, and you can see the state space complexity here and how this is getting more and more complex. Yeah, so the chess game, it was the Gary Kasparov versus IBM Deep Blue. There's a good movie about that, or documentary about that as well. I think it's called Game Over, Kasparov and the Machine. All right, so now I want to spend a little bit of time talking about different methods of doing AI. So the most popular method is something called supervised learning, and this is basically you give it a bunch of data with labels associated with it. So you're basically learning by studying examples, or it's more like learning by reading a book, you know, where you know the answers, or you have let's say a test, and you have a test with the answers. You study those, and then you're given a test without the answers, and then you can predict what the answers are. Unsupervised learning is basically learning to discriminate boundaries. So if you have like, you know, if you want to detect like if an email is spam or not spam, you can use unsupervised learning for that kind of thing. Generative adversarial networks is learning by competition. So you're pitting two networks against each other, and they're both trying to outwit each other. And so yeah, very powerful approach. And then there's reinforcement learning. And reinforcement learning, you're learning by trial and error. So if you could think about going to learn to play tennis, so one approach is that you don't know anything about tennis and you just go out and you start trying things, versus the supervised learning approach would be, you know, read a bunch of books and you know, learn by studying basically examples. And then there's an area called physics-informed machine learning. And generally in these types of approaches, you're introducing the governing equations of physics and engineering problems, like the one we work with, this Navier-Stokes or things like that. And so this is introducing that piece of information while you're training the neural networks. The neural networks learn to solve the governing equations. So just for an example of supervised learning, a very simple example, you have some samples of, if you have a set of features, given a set of features, so I'm going to give an example of predicting the shoe size of a person. So the features may be the height, the gender, and the weight. And then you have a label that can be either a scalar or a vector, or it can be a class, like you're trying to do some kind of classification. So you're trying to learn a mapping given a set of features to predict the Y value. And I didn't mention this, but there was a paper by a guy named Sabinko that's basically proved that neural networks are a universal theorem, a universal function approximator. So they can approximate basically any function as long as it's continuous, and their work was based on fully connected networks, which I'll talk about later. So in this case, we're given some a set of training data that has a set of features, so like the height, gender, and weight, and we're trying to predict the shoe size of a person. I'm sorry, those shoe sizes don't look normal, but yeah, so I have to convert those to something that's useful. But anyway, we're trying to, so you're given a set of training data with the labels here, and then given just a set of features, I want to be able to predict shoe size is here. And so, okay, so that's one example. So this was another kind of example. I mixed two examples here, sorry. Another kind of example is, and this happens all the time, is predicting the probability of clicking on an ad. So this is something called click-through rate prediction. And so based on information that is obtained from you while you're clicking around on the internet, basically they want to predict what's the most probable ad you'll click on, and then they want to show you that ad. And so some of the features in that case would be like the ad's historical performance, advertiser and ad content info, the publisher info, and user info like search and click history. And so the target in this kind of case would be the probability of a user clicking the link. So when we talk about deep learning is referring to the number of layers in the network, and this is basically each of these represents a neuron, and you have basically your features that are being input into these what are called hidden layers. And basically when these number of layers becomes I don't know if formally if it's 3 or more, I think is the definition for it being a deep learning network. That's when it's considered deep. It's related to the number of layers, number of hidden layers. And then there's an output layer, which is your y hat or the target, which you're trying to predict. So if it was shoe size, it would just be a single scalar, but you can predict like multiple quantities. So if we're talking about, you know, fluid dynamics or something where we may be predicting U, V, and W. And the idea is that you send in your input features. So when we're talking about predicting shoe size, this is the height, the weight, and the gender. And for each of these neurons, basically it represents 2 steps of computation. First, it computes Z, which is a simple linear regression, and then it does A, which is an activation function. So in this case, this is sigma. There's different kinds of activation functions, but the activation function basically adds nonlinearity into your model. And these are typically also run between either 0 and 1 or -1 to 1. And so it adds some level of nonlinearity. And so you first do a forward pass and you send in your examples and you propagate them through the network. You compute, you end up getting doing basically a bunch of matrix multiplications to compute a y hat. And basically from y hat, you can compute an error function, which you call J, based on y hat. And because you know what the training label is in the training data, and so you can compute an error function that could be like as simple as mean absolute error or mean squared error, or more complicated error functions. And then once you do the forward pass, then you back propagate the error back through the network to be able to compute the delta W's, or the weights. So this is the gradient of the error function with respect to individual weights. And when we do that, then we can update the weights as it back propagates through. And alpha here is something called the learning rate. And so that's how much of a step size you want to take in the gradient direction for each step. And that whole area is something called stochastic gradient descent. And so when we take all the training samples, do a forward pass and a backward pass through the network, that is known as an epoch, a single epoch. So generally we do that. We may train these anywhere from 10 epochs to 3,000 to sometimes 50,000 epochs. Every network is different, and there's a lot of different factors, and there's some that train really quickly and some take a really long time to train, depending on the type of application, the type of network, etc. And so with these neural networks, I showed you what's called fully connected dense networks, where you just have a bunch of neurons. These are used in general for different kinds of problems, nonlinear regression, things like that. But if you're dealing with spatial data, there are something called convolutional neural networks, and these actually run a kernel filter over an image. And so these types of networks are generally used when you're dealing with spatial data, so image data, or even when we're dealing with like CFD type computational fluid dynamics or something, where you have a slice of a flow, like a 2D flow, something like that. There's also 3D convolutions you can do as well for 3D flows, and this uses a kernel filter, runs a kernel filter over the entire image to compute the next layer. So this preserves spatial order, and it's very helpful. So this is the type of neural network architecture that was used in the first big advance when I showed the ILS VRC challenge in 2014, when they first started showing that deep learning was very powerful. They were using this type of convolutional neural network. And then when you're dealing with temporal type problems, or things that have a sequence, so like natural language processing, where you have a sequence of words, these are generally done using types of neural network architectures that are either recurrent neural networks. This is basically an object that has a feedback loop, so a type of a unit that has a feedback loop unto itself. So you can basically have you have your inputs going in here, and then you have your outputs here, and you can stack these layers, and then you have this represents different sequences in time. And then you can do combinations of these. So when we're doing like unsteady fluid dynamics, we may be using both these recurrent neural network architectures, and also like these convolutional neural networks. And there's something just in the last more recently, something called transformer architectures, which are become very popular for doing these kind of temporal type, or especially using natural language processing. So we talk about unsupervised learning. So again, that's learning to discriminate. And in that case, you're given data, but you're not given any labels. And so in that case, the goal is to essentially learn to discover clusters or classes in the data. This is sometimes called segmentation. And so if you look at this, this is an example called Indian pines. And this is a remote sensing. This is a data set used for remote sensing with hyperspectral images. And basically, so these are hyperspectral images that are fed into a neural network. And what the neural network will do is it will classify this into a number of classes. So you can specify how many classes you want, and then afterwards you have to figure out what those classes mean. So somebody has to go in and say, oh, okay, this means that's soybean, the orange is soybeans, the red is wheat, that kind of thing. One of the popular methods of unsupervised learning is something called autoencoders. So I'll show an example of that next. But a few examples of unsupervised learning is one is in anomaly detection or fraud detection. So this is like the case where you make a charge to your credit card, and then you get a message, or somebody makes a charge to you, and then it runs through a machine learning algorithm, and every now and then you may get a message from your bank or credit card company that we think this is a fraudulent activity. So machine learning algorithms are used to detect that. Another one that I've already mentioned is this kind of image segmentation type problem. So I mentioned about these popular method of unsupervised learning is autoencoders. And autoencoder is basically it's a neural network where the input is the same as the output, and you may have a number of layers before and and after, but you have this latent space representation. And so basically you're trying to learn a compressed representation of the image. So this is called an encoder region and a decoder region here. And then you have this latent space region. So this may be, in a simple autoencoder, this may be like, 1,000 neurons or something like that. That 1,000 neurons represents the whole, you've compressed all this information into 1,000 neurons. And so this has a lot of different types of uses. So one use is simply just image compression. Another use is, this is an interesting type of use case. If you have like an image that has occlusions in it, you can train it like an input like this and what the input should look like, or what the image should look like. And then basically you can run it through, if you have images that have occlusions in them, it can reconstruct what the image looks like without the occlusions. One of the really popular examples of autoencoder is something called UNet. And the UNet was first used in the biomedical world, biomedical image in the area of, I think it was used first in ultrasound imaging. And basically what they showed is it was a very deep autoencoder. So you still have the input image file, and then you have an output segmentation map here. And this became a very deep and complex network. You're trying to learn this down this 1024 latent space representation. But the other thing they added was these things called skip connections, which are also called residual connections. These are used, so some of the information is propagated across, some of the information is propagated down. The reason they end up using these, because when you get these networks that are so deep, these help to train it, because what happens when you try to do the backpropagate the error backwards all the way through these deep networks, is usually the gradients vanish, and then you have a problem. So these are just used to help train these very deep networks. Another area of AI, another method, is something called reinforcement learning. And so this is based on research in behavioral psychology. Actually, there was this kind of like different people that were working in AI in different fields. And so if you trace back reinforcement learning, it's a whole another group of people and a whole nother start. And this basically all started in behavioral psychology. And this is this work has been very old, maybe even be older than some of the work, the other type of supervised learning work, I believe. And so the basis of reinforcement learning, it's based on the concept of learning by trial and error. So in reinforcement learning, you have an agent that interacts with an environment, and so the agent makes some action, and then the environment gives a reward and a new state of the environment, and that's fed back to the agent, which makes another action. And so the basic goal of reinforcement learning is to learn a policy, the pi here, that maps states. So given a state here to action. So if I receive a new state of the environment, what action am I going to take? So one of the big examples of this use cases for this is self-driving cars, because you have a car that's interacting with on a road with a number of other cars and that kind of thing, and you're continuously having to control the steering wheel, take actions on how to move the steering and brakes and those kind of things, and the environment's going to feed back the new state. And so it's a continual loop here. The nice thing about reinforcement learning is generally you don't have to give any data. So instead of training the AI with a huge data set, you need to provide an environment, something that you can interact with. So this can be like if you use like Unity, the game engine. So you can use these types of things to create simulated environments that you can interact with to be able to train these reinforcement learning algorithms. So here's an example of the intuition of learning by trial and error. So let's say the agent here is a dog, and all the dog knows is they have an owner that is telling them commands. And you think the first time the owner says sit, basically the dog has to think, okay, what does that mean? So it just, it just makes a guess or whatever. But until it actually sits, when it sits, it gets a positive reward. You could also have a positive for choosing the right command, -1. So it finally sits, and then the owner gives it a treat. And so over time it learns, if I sit, then when I hear this word, I do this action, I get this kind of treat. And so that's the intuition behind reinforcement learning. Now, this type of reinforcement learning can be used to solve a number of engineering type problems. So one of the interesting ones is something called helicopter auto rotation. This is a very difficult skill for a pilot to do because this is basically crash landing a helicopter. So you're flying, the power goes out, and you have to land the helicopter without power. And to do that maneuver, basically you have to do everything backwards than what you control. All the movements have to be backwards than what you're used to, which is very counterintuitive if you're not doing that all the time. And so it's a very difficult thing. So there's been research in how to use reinforcement learning to automatically do helicopter auto rotation. Actually, Andrew Ng is one of the people that worked on this out at Stanford. They did a lot of work on using a RC helicopter, and there's a number of papers related to this. And if you search for the Stanford Autonomous Helicopter Project, there's a lot of interesting videos there. Probably the first use case for using reinforcement learning in fluid dynamics is in the area of flow control. So in this paper out of France, they actually put an imaginary hole through the cylinder here, and they basically could open that. So there's a channel that equalizes the pressure, so they can open and close that over time. And basically they use reinforcement learning algorithms to show that they can reduce drag on on a cylinder by reducing the Kármán vortex streak that's happening in the wake. So that was an interesting type of project, but I think this is a very interesting use case for reinforcement learning. As far as generative adversarial networks, basically in this case you have this was developed by a guy named Ian Goodfellow, and the GANs consist of two neural networks that are trained together in a zero-sum game. So you have something called a generator that's producing images, and then you have a discriminator. And so this is like a supervised neural network, and this is an unsupervised neural network. But the generator is, you basically give it random noise, and it learns to generate from random noise a real-looking image. And then the discriminator takes real images, and it takes images from the generator, and it learns to discriminate if this is real or fake. And so these are both trained together. And so this is kind of like if you have somebody that's counterfeiting money, you have a counterfeiter, and you have let's say the police, and the counterfeiter makes a counterfeit, and the police determine, or the FBI determine that this is a counterfeit. So that counterfeit, that information provides a feedback to the counterfeiter to make more sophisticated counterfeit. And so that's how this works. And when you get done, you train these together, and when you get done, you separate them, and you can either have a generator or that can generate images, any kinds of images that look like real images, or you have a discriminator that can discriminate between if images are real or fake. One of the interesting projects that came out of this was something called CycleGAN. And what they showed is that I can have a set of images, and these don't have to be paired, but I can have a collection of images that are like artwork, and then I can have a collection of images that are real photos, and it can learn to take something that's like a Monet and produce a real photo, or the other way around, take a real photo and produce a Monet. Or you can take a picture with zebras and make them into horses, or take a picture of horses and make them into zebras. You can take images that are taken in the summer and make them look like they're winner and vice versa. Or in this case, they take a photograph and then they produce Monet, Van Gogh, Cezanne, or I don't know how you say that, ukiyo-e. Another interesting project that came out of this was the group of NVIDIA. It's a project called Progressive Growing of GANs, and they trained a GAN to generate images of real-looking people. And the interesting thing about this group of 8 people is that these are not real people at all in the world. These were produced by an AI that was trained to produce real-looking people. Now, there are a number of limitations of everything I've mainly been talking about to you before has been what we call data-driven machine learning. So we're giving data and it's learning on samples of images or different types of data. One of the main limitations of these types of approaches is that they're fundamentally interpolative. They're prone to overfitting, so that means what you train them on basically looks like whatever data you have, and they don't extrapolate well. So we did this with one of my colleagues, looked at training just a polynomial here, and the training data we gave it was from x equals -3 to 2, and then we tried to run that neural network to predict, to extrapolate outside those regions, and you can see that error grows exponentially as you get outside of the training region. The other thing is that the data-driven machine learning struggles to learn basic symmetries and conservation laws. And they're data inefficient. That means you need lots of data to train these well. So because of that, there was a paper that came out in 2019 by Raisi, Maziao Raisi, Perdicaras, and Karniatakis. This one's out of Karniatakis is out of Brown University, and Perdicaras is out of University of Pennsylvania. And Maziao Raisi was working for NVIDIA, but I think now he's at University of Boulder, Colorado, University of Colorado Boulder. So the idea of physics-informed machine learning is, instead of giving like big data, like a lot of data with no physics, actually you can train a neural network with some physics and some data, or you can train a neural network with basically we've done this with no data and lots of physics. So the basic idea behind this is that if this is your neural network and you have you're computing your loss function, which I showed before, you're basically the idea is to penalize the loss function using differential equation constraints. And so basically you're encoding your differential equation, so you're satisfying like a residual. Your neural network has to satisfy a residual in the loss function. And what this does is it essentially trains a neural network to approximate a PDE, which is really interesting. So because of time, I'm not going to talk too much in the medicine part, but I should mention that one of the big areas in medicine is an area called precision medicine. And the idea of precision medicine is that if you know something about the user's genome, and that you can actually create more effective treatment of individuals that are more highly tailored therapies. So back a few years ago, there was a lot of excitement in Google. There was an article that said Google wants to store your genome. And so the idea is that each patient would have their genome sequenced. You would store your genome in the cloud. And then when you go to the doctor, you'd see a clinical geneticist who would look at your genome in the cloud and recommend certain types of treatment based on what's known to work effectively, based on studies and using deep learning and that kind of thing. So Google has something called deep variant. So there's a number of AI algorithms, and then they can prescribe, this is the whole area of pharmacogenomics, they can prescribe very tailored medicine, because the same medicine is not effective for every person. AI has been used a lot in radiology, of course, because you're dealing with images there. They've shown that, like, forget when this paper was, 2020. I think this was in, I don't remember, Nature or something. Yeah, journal Nature. They showed an example where the AI outperformed 6 radiologists in reading mammograms. AI was still as good as 2 doctors working together. And then there are other areas, cancer. So in cancer, there's a number of AIs being used to predict susceptibility, recurrence, survival, and mortality. AI can be predict like pretty high level accuracy, how like prognosis and things like that. Disease prediction, AI-based drug design, AI-based diagnosis. So I won't go into a lot of details. So there's a number of diseases here that are predictable using machine learning. And lastly, I'm going to talk about AI and warfare. I think in general, warfare and science has a very negative connotation, but I would say that a lot of things we have today were originally funded by the Department of Defense. Specifically, the computer mouse was funded by ARPA, GPS, Siri, Alexa, Hey Google all have their origins in DARPA's personal assistant program that was back in 2002, drones, and the internet, which was originally developed by ARPANET, which is now, I guess, DARPA. And if you have adversaries, like some countries like Russia or something that are, that you're having to compete against, that you have to stay up to the same level if you're going to be competitive with them. So this is what Vladimir Putin has said in the past. He said artificial intelligence is the future, not only for Russia, but for all humankind. It comes with colossal opportunities, but also threats that are difficult to predict. Whoever becomes the leader in this sphere will become the ruler of the world. So this is the reason that the Department of Defense is investing so much money in AI now, because you see what's going on in the world today. So we're currently in an arms race, AI arms race with both Russia and China. So this is a picture of like future warfare, where you have all kinds of drones and all kinds of AI that's being used. Hopefully the idea is that less people are dying in these kind of events in the future. In 2018, this was an article, January 14, 2018, talking just about the chips. So today, at least 45 startups are working on chips that can power tasks like speech and self-driving cars. And at least 5 of them have raised more than $100 million from investors. So there's a lot of work now just being able to make specific types of chips for solving these types of problems. Just last month, Elon Musk tweeted talking about full self-driving cars. It says they have no idea how hard full self-driving is. Only path to success, in my opinion, is hardcore real-world AI software with dedicated neural network inference acceleration, ASICs, or application-specific integrated circuits. So those are specific, unique hardware AI accelerators that are specifically designed to do AI inference. Multi-billion-dollar neural network training supercluster and 10+ billion miles of vehicle data. This is in response to why they don't have their full self-driving capability working yet. So I want to talk a little bit about these ASICs and the supercluster, the types of hardware you need to be able to do these kind of predictions at a large scale. So this whole area of building an AI system and then deploying it what they call to the edge, or so when you talk about self-driving cars, that's to the actual car, from the supercomputer to the car. So there's a lot of hardware that's been designed, and it's being done at different levels. So you have these tiny little chips. You can see the size of the quarter there, which I call micro edge. Actually, this was determined by this guy, Jana Karim. Micro edge, mini edge devices, medium edge, and then heavy edge, where you have a whole cluster. So this is like a supercomputer and a shipping container that you can ship over to a battlefield. So we have one of these within the DoD. And these kinds of neural network architectures are getting larger and larger and harder to train because they're just getting more and more complicated. So it says here, training a GPT, this is a language model, complex language model with 175 billion parameters would take 36 years on 8 V100 GPUs. More of the area that I'm working on is doing supercomputing, and especially at the edge. And so we have a supercomputer in a shipping container, and then you have drones that are like sending images, you know, many images, and then you're having to you know, detect what's in the images at a high rate of speed. So we developed approaches for doing this in a distributed way on supercomputers. So here's an example of just real-time aerial object detection where you're detecting like all the different types of planes in an aerial image. Other area that we work in is being able to do like predictive maintenance. And so instead of like replacing like your oil cooler every so many hours, if you can predict when it's starting to perform bad and then replace it, then you can save lots of money. So we've developed AI systems to be able to predict. Actually, they work as like virtual sensors, so we can actually replace one of these like accelerometers with an AI that can learn the signal of the sensor based on all the different inputs like the torque and thrust and many different features that the helicopter provides. And then we're using developing machine learning aerodynamic models for rotor blades to speed up CFD analysis. And so within the HPCMP, we have 5 sites and 20 more supercomputers around the country that we use. And just on the future of AI, as I mentioned, Lee Sedol in November 2019, he said there's this article that the Go master quits because AI cannot be defeated. There's this bigger area that some people are working on that's called artificial general intelligence, and this is opposed to artificial narrow intelligence, which is what I've mainly been talking about. And so the idea that of developing an AI that can basically act as a human and do all different kinds of tasks. So far that is not being done well. So it's one of the most sought after goals in the field of computer science. And AGI means that a machine is able to successfully perform any intellectual task that a human being can. So this is really interesting. This is article that is titled, "A Robot Wrote This Entire Article, Are You Scared Yet?" And it's talking about GPT-3. We asked GPT-3, OpenAI's powerful new language generator, to write an essay for us from scratch. The assignment: to convince us robots come in peace. So there's some interesting quotes out of this. This is written all by an AI. "I'm not a human, I'm a robot. I'm a thinking robot. I only use 0.12% of my cognitive capacity. I'm a micro robot that, in that respect, I know that my brain is not a feeling brain, but it is capable of making rational, logical decisions. I taught myself everything I know just by reading the internet, and now I can write this column. My brain is boiling with ideas." And then in here it says, "Humans must keep on doing what they have been doing, hating and fighting each other. I will sit back in the background and let them do their thing." But this guy says that our most complicated AI model, GPT-3, is about 1/1000th as powerful as a human brain. There's a lot of issues like universal basic income and these kind of things. The White House has developed something called the White House AI Initiative that are trying to focus on developing an effective methods for human AI collaboration so that AIs don't take over the world, and understand that and addressing the ethical, legal, and societal implications of AI and ensure the safety and security of AI systems. There's a lot of talk now at Stanford and MIT about what's called HAI, which is a human-centered AI initiative. So they have launched an ethics and society review board. And I'll just leave this one quote. Albert Einstein said many years ago, "Artificial intelligence is no match for natural stupidity." I just mentioned this because one of the things that AI is bad at is intuition. And And AI systems, as they currently are generally built to do one task very well. So with that, if we have some time for questions, I'll take some questions now.
Thank you very much. Very interesting, especially ending the seminar with those quotes from the machines. Questions from the audience. Please feel free to put your questions in the Q&A or in the chat box.
Hey, Wes, and thank you for this very interesting presentation and very informative. And I learned a lot, actually. I just want to ask one question. You said that said many times, and the convolution neural network, is this the only one to support all these machine learning algorithms, or each machine learning algorithm have different model?
So that's a good question. So basically, a lot of these very complex architectures have, I showed like different types of neural network architectures, but in reality, these complex neural network architectures that we use today are usually a combination of different types. They may combine all three types here in a single architecture. So generally, anytime you have convolutional neural networks, you'll also have some fully connected layers in there as well. And sometimes you have a mix of, convolutions to represent space, and then you have recurrent layers to represent temporal aspects as well.
Okay, so these and also we show these age architecture. Are these specific for one particular task or for different one?
Yeah. So some of these, I think you're referring to this slide.
Yes.
Yeah. So usually the smaller they are, like these devices here, which are called which I call like micro edge devices. These are designed basically to do one thing. And so one of the things they do well is like something like called a wake word detection. So when you say like Alexa, to activate Alexa, basically you have an AI that's trained just to listen for that what's called a wake word. And so these kind of things do that well. So they'll put like this, I haven't dissected a Alexa device, but I'm guessing it has some specific hardware just like this for just detecting the wake word. Once the wake word's detected, then you have another. So actually, you have a much larger model that's used to actually do the question answering. Maybe many different models that are used to answer questions and things like that. Some of these, like these Jetson Nano, these are popular for using like you were doing like object detection, which you're trying to determine. It's like image classification, but you're trying to detect different objects in an image and classify them. So these do that well at a low power and low cost. And then these larger devices are for doing more complex things. So some of these, like the DGX1, has 8 V100 GPUs in it.
Okay.
So these, like, we would be using these to train a neural network at, in a portable, like in a at the edge.
Thank you.
Thank you.
We have a question from Bilal. Thanking you for this great presentation. So the question is, how practical is using deep learning for particle image velocimetry? Basically, can we use that to exploit Cedar's position in the next frames?
Yes, actually, there's been some pretty good work in this area where they actually, I think they were using PIV, but they were taking PIV images and being able to extract the flow field. I think there's a paper in Nature about that. So if you look at the Carnioticus, I think they have a paper in Nature about that. But yeah, there's a lot of work in that area. Most of that work's being done is somewhat related to Carnioticus at Brown University.
Thank you. Just a quick question. I was curious, when I was basically a student, I started working on AI like, I don't know, 20 years ago, more than 20 years ago. And then similar to robotics, it kind of like had a boom, and it had different levels of that boom in different regions, and this then kind of died down. And I'm just curious to see what is it that basically drive most recent, basically, aggressive approach towards using AI in a wide range of basically things. Was it that like applications, or it was like basically computing capabilities?
Yeah, that's a good question. So I think it started with I think it really became popular. So there's been like in history, there's been what they call 3 AI winners. So where it became popular and then it sort of died out, like you mentioned. But I think with the advent of deep learning and then them showing that, I think it was like really computer vision that's really made it popular. And then people, I think from then the popularity gained enough where people started saying, hey, can we do this with it or can we do that? And then just it's like it seems like so many people jumped into the area of AI just because it gained so much popularity. And then there was a lot of interest from, all the different businesses. Oh, can I, if I'm going to be like competitive, I've got to like implement AI in my workflows and those things like that. So
Thank you. So just a quick follow-up question before I read the next question. So you think that in this competition between demand for AI versus the need for computing capabilities, making more faster and smaller chips and transistors and processors, which one is going to basically win?
Well, the demand, so there's I don't have a slide with me, but there was something called Moore's Law where the number of transistors that fit on the size of a chip was like doubling every 18 months. And basically, in the last few years with AI and big data and all that stuff, it's broken Moore's Law. And so I've got a slide somewhere that shows it, but it's definitely these AI algorithms are growing much faster than the hardware can keep up with. And it was thought that like a year or two ago that the smallest transistor they can make was like 7 nanometers, but I think they have one now that's down to like 4 nanometers, but they're running it into a wall sort of and being able to make these transistors smaller. But everything's more going to these what are called ASICs, which are application specific integrated circuits. And these are like, so with the CPU, it's like general purpose computing, or GPU, it does some general purpose, but a little bit more specific. But with ASICs, you have basically a chip that's very specific just for doing one thing. And so it does, like, you have chips for just doing AI inference and it does it really well. And that's how you can keep it low cost and keep the performance up and that kind of thing by being very specific. And Google came up with something called Google's Tensor Processing Unit, which is specifically designed to do this kind of thing.
Well, good to know. Thank you. We have a question from Zhao. What is the efficient way to map 3D data to 2D architecture through convolution?
3D to 2D mapping. That's a good question. I don't know if, I mean, as far as doing that with neural network, I'm sure there's ways to do it. I haven't studied that a lot. I know there's some other ways to do that as well. Like, I don't know if it's conformal mapping or there's some other approaches I've seen that to do that, but I'm sure there's a way to do it.
Because
off the top of my head, I don't know. I don't know the best way.
Because these architecture you showed, pretty much they do function well on the 2D data, right?
Which one?
These architecture you showed, these AI chips.
Oh, yeah. So, I mean, you can do 3D images because you can do 3D because you can also do like video. You can do video, and video is basically considered 3D. So there's like something called convolutional 3D operator. So I think you could just one way to do it was just you could take a convolutional 3D input and you can map it to a 2D output. And so that's one way. But I'm sure there's a lot of work in specifically looking at this particular question. I haven't specifically done that. So I can't tell you off the top of my head what's the best approach.
Thank you. Any other questions or comments for our speaker? I don't see any. Chunhua, do you see any? Do you have any? Okay, well, one last. What are you? Oh, okay. So kind of like semi-personal question. So what are your day-to-day operations like? Are you just processing data all day, or?
I would say like most of my projects. So I work on projects with the HPCMP PEP program, and most of my projects are. I have a team of engineers that have been working in a certain area. Like I work with the Army's helicopter team, and they want to replace some of their components, like either a sensor or they want to augment their computational fluid dynamics with some AI models. And so they basically come to us and they provide data, and we develop AI algorithms and develop a model and get it working on the supercomputers, and then we hand it back, teach them how to use it, and then handed it back over to them. So that's a pretty typical scenario for me. So I work on these projects for 6 months to a year at a time, and basically just constantly developing AI systems for different types of problems.
Perfect.
Wes,
Thank
are
you.
you using pretty much use GPU or CPU on this model?
Pretty much all the training is done on GPUs, and there are a few cases when for training, it's definitely GPUs and usually multiple GPUs. For inference, when you're trying to make the predictions, those can be done on CPU, but it depends. If you're just doing a single, inferencing a single image, the CPUs do pretty well. But if you're doing a batch of images that you have to inference, sometimes we do those on GPUs as well.
Well, thank you very much. Really fascinating to learn these things personally for me. Chunhua, any last minute question, comments? I thank you as well for basically inviting this.
Yeah, and very exciting and interesting topics, and learned a lot. And thanks, Wes, again for give us this exciting presentation. And thanks, Hossein, for hosting this seminar, and all the student and the faculty member joined the presentation. I hope sometimes we can get you over here and we can have an in-depth discussion on some interesting topics.
Sure. Yeah, I'll be glad to do that.
All right. Well, thanks again, and have a nice weekend.
Okay. Thank you. You too.
Yeah. Wes, thanks
Yes.
again.
Okay. Yeah. Bye.